All right, we're going to talk about getting clean, and I guess in order to get clean, first you have to get dirty, but that's your business, okay? But anyhow, let's talk about how to clean it up once you make a mess. All right, I'm pretty good at making messes, so it's important to me that I know how to clean up. How do soaps and detergents work? Okay, well, basically, let's start off with what a fat or grease molecule is. Okay, ironically, we make soaps from fats. Okay, we start with a fat, and we treat it with a base, sodium hydroxide, NaOH. We should know how to pronounce that one right because we learned our rules on how to name them. Sodium hydroxide is a strong base, and when you treat a fat molecule with a base, it breaks into these three tails and a glycerol. Sometimes they're called fatty acids or soap molecules. Okay, and the glycerol that used to hook them together here. All right. Now, we're not so much worried about the glycerol. We're not worried about it, but we do want this tails, these three tails that we have here. Okay. All right, we have these tails. Now, the tails, the important thing is normally these are fats, basically, right? And so most of it is non-polar. Okay, all this part down here is non-polar, which means it does not mix well with water, right? All right, now when we had glycerol over here, this end was non-polar, but now when it broke off, it ends up with a sodium with a positive charge here. So guess what? This end is polar. Now it's not bipolar. There is no negative end to go with it. So it's not bipolar. Soap's not bipolar. It is only polar, but it has a polar end on it now. All right. So we have grease or dirt and stuff on our hands that are non-polar. We try to wash it with water, which is polar, and it doesn't mix, and therefore it doesn't come off and let go of your hand. But if we attack it with soap, then we get a little different thing here. All right. The non-polar end of these things attack or to the piece of grease or dirt because they do mix with it. Okay, the non-polar ends attracts like. They like the non-polar dirt, grease, or grime, or whatever, and so they attach onto it. Now, the part sticking out here is the sodium end that has little positive charges on it, and it is polar. Well, if it's polar, then water, which is also polar, will be attracted to it, and so the water molecules hook onto the edges of this piece of dirt. Okay, now since it's surrounded by water molecules, it can be picked up off your hand and it floats away along with all the rest of the water because these water things on the outside make a shield around it and they're attracted to this polar end sticking out around the dirt molecules. All right, if you've ever been washing dishes and you get to the last of the dishes and they just don't seem to clean very good, part of the problem may be you need to add more soap because all these polar molecules that attach onto it, the soap molecules that attach on, have already been used up, and there's not any more or not enough of them to attach on and lift off the dirt. So the non-polar dirt is attracted to that end of the soap molecule. The polar end of the soap molecule is attracted to the water, and that picks it off, and then it can go and leave leave your hands or whatever and washes off down the drain and you get rid of it. Okay? So ironically, it is used fat in the first place to make the soap molecules that eventually are used to take grease, fat, dirt, and stuff like that off of our hands. Generally speaking, we said soaps can be made from, the first ones were made from pot ash, the ashes from where they cooked their pots on the fire, and it was a base, and they used that to treat the fats, animal fats, to make soaps. Okay. Lye was another one, sodium hydroxide or lye. You hear about lye soap that people used to make back in pioneer days. So that's very strong stuff. But that was it. Now, technically, chemically, if it's a soap, it's made from natural ingredients. And if it's a detergent, it is synthetic or man-made. Okay. Now, that's not the difference between like hand soap and detergent. But generally, as chemists, when they're making either soaps for hand and body wash and all this other stuff, they're saying a soap is made from natural ingredients and a detergent is made from synthetic or man-made ingredients. Most of our cleaning agents and stuff are detergents nowadays because they're synthetic and man-made. They're cheaper, and generally they penetrate and get in and hook up onto the grease particles. They penetrate into it and hook on better than the ones that were made from man-made, from natural things. They've increased the ability of them to hook onto grease and dirt and things like that with some of their man-made ones. At one time, a lot of them were made with a phosphate group. You may hear about phosphate detergents. Okay, here's a couple of formulas. Here's their chain, but basically, this one has a sulfur there. This is sodium lauryl sulfate. This is a very common cleaner. You'll find it in shampoos and stuff like that, as well as toothpaste and other things that are trying to clean things off. This one is sulfonate. Okay, it's another common one. It has a sulfur here. There used to be some that the sulfur here had a phosphate group. Okay, a P there, phosphorus instead of sulfur, and they work very good for cleaners. But unfortunately, they cause a lot of pollution and cause problems when they're washed into the rivers, and they kind of fertilize them. And then you have these algae breakups, and the algae, not breakups, I'm sorry, algae blooms, where just tons of algae start growing, fertilize it like crazy. And then the algae would use up so much oxygen it would start killing off the fish. And so, anyhow, they basically cut back on that, and they found the sulfates work better for that. But you'll see sometimes on the side of a detergent or dishwashing soap or something, it'll say no phosphates. Okay, and that's true of all of them. It's not such a big deal now, but they'll still say that on the side sometimes, just to show that they still do not use the phosphates because they're more pollution. All right, the last stuff that we're going to look at having to do with solutions has to do with water treatment. Okay, we don't think about it a lot because we just turn on our faucet and water comes out, but that water has to have been treated in order to be potable. Okay, potable always sounds to me not really good, but water that is potable means that it is suitable for drinking and can also be used for showers and so forth. It's been treated, okay? If it's not potable, sometimes you'll be at a national park or state park or something, and it'll have some faucets that are not potable. In other words, if you're not going to drink the water, you can still use it for whatever you're going to use it for. But if you're going to drink it or cook with it, you don't want to use it, okay? But the water we have is considered to be potable, and that's because it has been treated, okay? And the whole point of water treatment, okay, not to be confused with sewer treatment. There are sewer treatment plants which take sewage and try to treat it to make it so that it can be released into lakes and rivers without causing any problems. But water treatment, even for the ones that we just water from a lake or well that we're going to drink, has been treated usually to make sure that there's no pathogens or impurities in it that are going to harm us. Okay, several things they do to do that. One is they can just run it through gravel and sand. Sometimes they'll also have charcoal layers, and as it goes through there, it will filter out, just like people use charcoal filters in their fish tanks. It'll get rid of a lot of the impurities and large stuff that will get filtered out as it goes through the sand and gravel and charcoal. All right. Another thing that they do sometimes is aeration, which just basically means you take the water up. Now this is done inside here, but inside the tank they bring the water up and they let it fall through the air basically. Sometimes they'll have little fountains that shoot the water up, okay? If you're in a sewage treatment plant, part of that is you increase the oxygen level of the water, which means there's more oxygen for bacteria to use to break down all the sewage and stuff like that that's in the water. If it's water treatment that you're going to drink, then a lot of times this allows things like sulfur compounds, hydrogen sulfide, which is the rotten egg smell. Some places have a lot of sulfur in the rock layers underground where the groundwater came from when they pumped out of the well. So this allows all those sulfur compounds that stink and smell bad to evaporate out. Okay, they're very volatile, which basically means they evaporate easily. And so a lot of those sulfur things will, as the water's falling down here, it allows that sulfur compounds to evaporate into the air and escape out of the water. So that's another good thing that they will do. Then usually it has been treated with disinfectants. Okay, sometimes it's chlorinated. Talk about chlorine in our water. I know I lived in Georgetown, and if you took the water we put it in a jar and set it in the refrigerator, and then if you opened it, you could smell the chlorine come off, but then the water tasted better because it had given time for the chlorine. It had pretty high chlorine levels because it was lake water, and so that would let the chlorine kind of settle out, and then we'd use that for our drinking water. In some places, they also use ozone. Ozone is basically just 3 oxygens hooked together. Okay, ozone is just O3. Okay, and if you bubble that through the water, it can be it will kill a lot of the biological things that might be in it, just like the chlorine will also. It's basically bleach. It will kill out those. Okay, some places, sometimes you can get portable ones. Okay, you put impure water in. There's UV light inside that zaps the water as it goes through to kill any bacteria and stuff that are in it, and it comes out the other end. A lot of people take these to camp and things like that, so they have a supply of water that's been treated to get rid of bacteria and things like that. Another thing that can be done to help clean the water will be different kind of tanks. All right, and there are some that are just settling tanks, which just allow big stuff that's in the water to settle out at the bottom. But then, like on this one, for example, they'll add lime, which is basically calcium hydroxide, and aluminum sulfate, and they mix these chemicals together. When they mix together, they make eventually aluminum hydroxide, which is kind of a gelatin type stuff. And as the gelatin stuff comes down, it captures impurities and stuff like that, get caught in it or attracted to it. And so as it settles out the bottom, the settling tank, besides just what would naturally settle on its own, this gelatin stuff settling out of it helps get a lot of that stuff out of it. And then they can just pump the water off the top, and it has been purified out of a lot of those things that could have been affecting it. Okay, there are some things though that are dissolved in the water. If they're dissolved in the water, this is not going to take them out. These are more things for large impurities. Like we said, things that can evaporate out can be taken out by the aeration. Okay. And like sulfur compound and stuff. The things that are actually dissolved, for example, lead or lead arsenic, a lot of those kind of compounds, if they get into the water, and this is why we try to guard the water table and the groundwater, because once things get into it, some of those are very difficult to treat and try to get out of. And so in specific locations where those might be a problem, perhaps they're located near a mine, old mining operation, that's a lot of problems up in the west, out in Colorado, places like that, then they may have to do special steps to try to get rid of those. Others, there may be things that are dissolved in them. For example, I live in Boyd, and there's some kind of sodium compounds in the water. Very strong, and it gives it kind of a funny taste. It's not a health problem, but it just doesn't taste very good. Okay, and so there are ways that they could probably get rid of that, but it would cost so much it's not really worth it, since it's not really a health problem. So that's just something you have to decide. Is it a matter of does it taste as good, doesn't look good, or is it really a health problem? If it's not a health problem, it may not be worth correcting that. But yeah, so that's another example of water in solution and things dissolving in it that we're trying to get out so that we can get the water to what we consider potable and that we can use as good for us to drink and use to cook and things like that. And that's pretty well it. Thank you for viewing, and we'll see you in Chapter 20.